everyone, my name is Pedro Costa. I'm a PhD student at Instituto Superior Técnico, Portugal, Lisbon. I'll be presenting our work, Tension Torsion Ultrasonic Fatigue Test on a Railway Wheel. Beginning to outline our presentation, we will first present the ultrasonic fatigue machine used and its basic concept and main components. Afterwards, we'll be talking about the basic concept and the testing material of the specimens, especially of the multi-axial specimen. Afterwards, we'll be presenting some finite element analysis and the objective of such analysis, and finalizing with experimental tests, some of the results and conclusions. So the ultrasonic fatigue machine we use is very similar to a standard uniaxial fatigue test that we also performed. Is composed by a booster, horn, and a test specimen, and they are excited by a transducer. On the right, you'll see the image of the testing machine. The specimen and the horn are the ones that have special design to create the tension torsion stress state. The horn receives actual displacement from piezoelectric transducer that transmits to the booster, that transmits to the horn, and this actual displacement is then transformed partially to rotation and actual displacement. From the two displacements transmitted by the horn to the specimen is then excited in a complex resonance mode composed by two modes that we specially designed to be within the range of frequency of work of the transducer. These modes are the first longitudinal mode and the third rotational mode. These were chosen in order to have one region with higher tension torsion stress. Here we can see both movements of each mode, the first longitudinal mode on the left and the third on the right. They are, when excited, in phase, and the highest point of stress is simultaneously achieved in the middle throat. Throughout our work, we have changed the geometry of the specimen, maintaining always the three-throat specimen. The final geometry we are using in this work is much simpler and much easier to machine, giving more consistent results. It's defined by 6 dimensions, and by altering the dimensions in a specific way, we can achieve a different shear actual stress state. Taking a look at the wheel in analysis, we made first a few tests to determine the young modulus, the density, and the hardness of the rim section, where we later machined the specimen directly as represented in the image. The metallurgic analysis of the rim as well as the web, since they are the main sections of the wheel, determined a perlite and ferrite microstructure. This analysis was very important to later understand the results we obtained in the ultrasonic fatigue test. After determining some material properties of the rim section of the wheel, many finite element analyses were performed using the whole set, horn, booster, and specimen for several different combinations of dimensions of the specimen, until a final geometry was obtained with the stress relation of von Mises. This stress relation was chosen in order to compare to already made conventional fatigue tests with a tension torsion relation of von Mises. So after many finite element analysis, a final geometry was obtained, presented in this slide. This geometry has the predicted 0.57 von Mises shear axial ratio. After machining the specimen, the thermal analysis test was firstly performed in order to understand if indeed we had a higher stress in the middle throat. looking at the images and the temperature generation, we can see that indeed the main stress region is in the main throat. After machining several specimens, both multi-axial tension torsion specimens and uniaxial tension compression specimens, they were tested in fatigue and then compared with conventional tests with the same stress cycles. Observing the results, we can see that ultrasonic fatigue results do increase the life, or for the same stress for higher stress we have the same life. From the literature and from comparing different results of different studies, we concluded the reason for this higher stress for the same life was related and connected to the prolific heat macrostructure, which increases such stress, but it also prevents the failure in a very high cycle fatigue region. So afterwards, we focused our work in comparing the angles and the fracture surfaces between specimens tested in conventional machines and tested in our ultrasonic fatigue machine. In this slide, we have a comparison between the uniaxial tension compression specimens, and we can observe various similarities between both specimens in the propagation and the initiation of the fatigue. Now comparing the multi-axial specimens also tested in conventional and ultrasonic fatigue machines and in-phase shear and axial stress with von Mises relation, there is an agreement between the fracture angles for both tests, and the initiation point and the propagation also show various similarities. We can, observing the images presented in this slide, we can clearly see the laminated shape related to shear damage, thus proving the existence of torsional damage in the ultrasonic fatigue machine built. Now for the conclusions, from all the finite element analysis and from the materials property study of the rim, we achieved a specimen geometry with the desired shear axial relation capable of being tested in a multi-axial state in ultrasonic fatigue frequencies. By observing and comparing all performed fatigue tests in conventional methods and in the ultrasonic methods presented in this work in two different states, the uniaxial tension compression state and the multi-axial tension compression torsion state, we can clearly see that the ferrite microstructure had an influence in the results, being that materials such that material shows to be sensitive. High frequency testing is led to a much higher stress for the same life and no failure in a very high cycle fatigue regime. Then comparing the fracture surfaces and fracture angles of both stress state specimens, we can see similarities between both methods, showing the same stress state being applied and creating the fatigue damage. Thank you for all your attention.